Have you ever seen the amazing sculptures of Julien Vos-André? He uses the slicing technique to produce all kinds of sculptures and people. For example, this one, I have seen it at the University of Minnesota campus. And if you move right in front of the sculpture, you can actually see right through. It's really amazing. And so this slicing method is exactly what we plan to do now, to find volumes or areas or some other information about a more complicated system. I will not be able to do the full human body, but I can do a rod. A rod. Well, that sounds a bit boring, but anyways, let's start with a rod. So the idea is we have a rod, rather long and thin and small. We would like to know the total mass of this rod, but the mass is not uniformly distributed along the rod. So there's a density distribution, and the density is called rho. And we can plot this on top of this rod. And so then the density profile is a decaying exponential. So this would be this one, e to the minus 0.1x. So this is rho of x. And now we would like to know the mass, total mass of this rod. But still, a rod is a little bit boring. How about we look at a Coco Roll? Here's a Coco Roll, and these are filled with a pistachio filling. And we could assume that this Coco Roll has a length of 1 meter. That sounds yummy. And the filling, the pistachio filling, is not uniform. So maybe the baker had more pistachio in the beginning than in the end. And so let's assume this rho is the concentration of the pistachio filling. And so then I would like to know how much pistachio is in this rod. So either way, if you like engineering, you talk about metal rods or something. And if you like baking, like I do, then you talk about pistachio filling. Let's add some numbers here. So the length of this rod is 100 centimeters, and the area, so meaning this area, if you look from the very front, is 5 centimeters square. So now we're going to use the slicing method to find the total mass of this rod. So which means we take a small element here, which we call dx. And the mass in this little volume, the mass is density times volume. So for this little purple element, I call the mass dm, right? I use the d notation for small elements. So then this would be the density, which is rho of x, times the volume. And the volume of this element would be the area, A, times dx. Let's just quickly look at the units. So the density has gram per centimeter cubed. An area would be centimeter square. And the dx is centimeters, so together this has a unit of gram, which makes a lot of sense for the rod. It also makes a lot of sense for the pistachios. Let's put in the numbers. So then rho was e to the minus 0.1x. The area was 5 centimeters squared, and the dx remains. This will be the dx. So then the small volume slice indicated there has this mass. And then the total mass, make it over here, would be just the integration over all these little mass bits dm. And now I make it into a definite integral because I know I integrate from 0 to 100, the total length of my rod, and then 5 e to the minus 0.1x dx. So now it's a beautiful exponential integral, which we should be able to do. So we find the antiderivative, which is minus 5 divided by 0.1 e to the minus 0.1x, evaluated between 0 and 100. So then I have 50, 1 minus e to the minus 10. Now e to the minus 10 is like a super small number, so this is basically 50. So you could say the rod has a mass of 50 grams, or what I would say is the Coco Roll has a total pistachio content of 50 grams. Delicious. Hey, Dr. Hillen. Hey, Dr. Hillen. Oh, Tolo is coming. Okay. Hi. Oh, you look funny, Tolo. Yeah, just move your head a little bit to the side, then you can see me. Very smart.